This is Lab 4, Circuits by Iishim Oberoi. The purpose of this lab is to predict the behavior of circuits with resistors in series and parallel, and to examine the behavior of ohmic capacitors in circuits. The takeaway from this lab is to understand how basic real-world circuits work and how different components affect their function. The main physics principles in this lab are the node rule, Ohm's law, and the potential difference of a capacitor. The main results from this lab were that the simulated circuit current was 0.02 amps, the high resistant bulb made the capacitor take longer to charge than the low resistant bulb, and the low resistant bulb dimmed faster than the higher resistance one. The model we're using is a simple circuit model with a couple different variations depending on our experiment. Our assumptions are that the system is the circuit and surroundings is everything else, that the wires have no resistance, and there is perfect transfer energy, i.e. no heat loss. The first part of this experiment was completed in the simulated CCK circuit lab. So our predicted values for the first simple circuit was 0.0204 amps according to the calculations shown, and our actual value is 0.02 amps. And if our ammeters were flipped, we would have a value of negative 0.02 amps. The next part of the experiment is when we open up the circuit. Our voltmeter measured a value of 3 volts, and our ammeter measured a value of 0 amps. The ammeter reads 0 because there is no current flowing through because the current circuit is open, and the voltmeter reads 3 volts because that's the potential difference created by the batteries. Closing the previous circuit and measuring the potential difference across different areas, we have AB as 3 volts, CD as negative 0.96 volts, EF as negative 2.04 volts, and all the rest of the segments as 0 volt difference. Now, adding all that up, we have a sum total of 0, which is expected due to the round-trip rule, and the current is still 0.02 amps. This is a graphical representation of our values represented on the last slide. As you can see, after the battery at point B, it goes up to 3 volts, the highest potential difference, or the highest potential, and then after passing through the first resistor, it decreases, and then after passing through the 100 ohm resistor, it decreases down to 0, which it then can go back through the battery and be pumped back up to 3 volts. Now, setting an ammeter in parallel to a resistor, we notice that the current measured by that ammeter in parallel is much lower. This is because the node rule dictates that the current must split and pass through each wire segment individually. So the current is split at that section, and then it is passed through, which leads to a lower reading. For the resistance calculations, we see that the resistance calculated for the 47 ohm and 100 ohm resistors is slightly higher than its actual value. This discrepancy is due to the lack of accuracy in the ammeters and not being able to measure the exact current properly. The second part of our lab was conducted in person with real circuits. For the battery plus RC circuit section, we saw that the light starts bright and then dims down as the current decreases to 0. For the RC circuit only, we noticed that again the light starts bright and then dims down to 0. For our 70 ohm bulb, it took 70 seconds to charge the capacitor and 66 seconds to discharge the capacitor. For the 30 ohm bulb, it was 15 seconds to charge and 14 seconds to discharge. Note that we didn't have a 10 and 20 ohm bulb like instructions said, we only had 30 and 70. Using the 70 ohm bulb in the RC circuit, we took 30 seconds of data and measured how the voltage decreased over time. We then plotted the ln of the voltage versus voltage initial and graphed that. Now, to calculate the RC constant, we knew from our lab doc that the ln of the delta V over delta V initial was the slope of our linearized line, and that was equal to negative t over the RC constant, where t was equal to 1. Plugging those two things in, we found that the RC constant was 43.478 seconds. Some sources of error in this lab is that we had difficulty measuring the voltage with the voltmeter prongs. There was possibly faulty equipment. There could be leaking of energy via heat in the bulbs, and the wire resistance in the wires and also our equipment of our voltmeter could not be completely negligible. For the first what-if question, we are discussing the simulated portion of this lab. So if a real ammeter was used in a real circuit, the ammeter would have some resistance, so the current would decrease slightly. And also the values would be less accurate due to energy loss through heat or chemical reactions in the battery running out. The second what-if question deals with our real-life RC circuit, so if we had charged the capacitor in a simulated circuit, the question is how long would it take compared to our real circuit. If we'd done it simulatedly, then the time to discharge would be a lot longer because the virtual simulation would eliminate all sources of error.